Hi there, my name is Bryce Lindsey, and today I'll be talking about the development and deployment of a mobile infrasonic data acquisition unit. Really quick, I'd like to thank my co-authors Brandon White, Dr. Brian Elbing, and Dr. Imran Farouk, not only for this project, but also for their constant guidance and leadership throughout my research and studies. So let's dive in. This data acquisition unit is geared towards primarily analyzing severe storms, so let's provide some context and talk about tornadoes here for a second. Tornadoes are violently rotating columns of air, and as you can see in this figure to the right, the tornadoes themselves are fairly small compared to the supercells that produce them. Tornadoes can produce wind speeds well over 200 miles per hour and be on the ground for quite some time. They're very dangerous, potentially lethal, and they cause hundreds of millions of dollars in damages every year. Right now, radar is used for identification of a tornado, but we still need storm trackers on the ground to provide the confirmation. To further develop the context of this presentation, let's talk about infrasound really quick. Infrasound is just sound below the typical human audible spectrum, and recently, infrasound has been an observed byproduct of tornadogenesis. This is exciting because this potentially eliminates the need for visual confirmation for storm trackers on the ground to confirm that a tornado has been formed. Right now, there's few data points on this phenomenon, so that was one of the motivating factors behind this project. A little background about the infrasound project here at Oklahoma State. This figure here shows our existing array. We've had this array for a couple years now, and it consists of 3 microphones. These 3 microphones are routed to our DAC via underground cables, so the array is stationary. Elbing et al. Lays the foundation for tornado-generated infrasound, and this figure on the bottom right is pulled from that paper. Here you can see in blue data collected before a tornado, and then here is data collected during a tornado, and it displays a swell of infrasound. These 3 mics in our existing array can use coherence methods to mitigate some noise, and they all 3 are the Chaparral Physics Model 24 microphone, which we will elaborate on shortly. One of the limits of our existing array is the fact that it is stationary, and that leads us into talking about Glinda. Alright, so Glinda, which stands for Ground-Based Local Infrasound Data Acquisition, is a mobile infrasound detection package that was deployed in the News 9 storm tracking vehicle out of Oklahoma City. There are several advantages to having that mobility, but the primary objective here was to increase the number of weather-induced infrasound data points. Additionally, close-range measurements could mitigate atmospheric propagation uncertainties. Some of the driving constraints when designing Glinda was we needed to have a resolution better than 20 millipascals to handle the noise floor, and that 20 millipascals is pulled mainly from observations from our existing fixed array. Additionally, we want to be able to collect supplemental data for the state of the vehicle, such as location, velocity, and heading. So here we have how Glinda is configured in the storm tracking vehicle itself. In this figure, you can kind of see all the components of Glinda. It is all sitting in the rear floorboard of the truck. Here label number 1 is the computer and sensor box, kind of where all the guts are. Label number 2 is our microphone. It's the Chaparral Physics Model 24, the same microphone that we use in our fixed array. And then label number 3 is the power supply. Now Glinda does not demand that much power, but those power supplies were already in the truck, powering other pieces of equipment for the storm tracker, so we went ahead and just tapped into his existing power supplies. So big picture view here of the application of Glinda. Here at the root we have some fascinating input from the universe that induces a tornado. That tornado does a lot of different things, but one of the things that it does that we're most interested in is it produces some acoustic dynamics. Those acoustics propagate through the atmosphere, eventually being picked up by our microphone, which we have to calibrate for and analyze the microphone dynamics. So diving into the components of Glinda here, as the onboard controller, we have a Raspberry Pi 3 running a standard distribution of Raspbian. Additionally, we have a GPS board sampled at 1 Hz, and we have a 10 degrees of freedom IMU sampled at 100 Hz. This IMU consists of gyro, compass, and accelerometer data, as well as ambient temperature and pressure. So moving on to the microphone specifications for Glinda. Glinda uses the Chaparral Physics Model 24 microphone, as we previously talked about, and here to the right you can see a typical frequency response for this microphone, and note the nice flat response at low frequencies. This microphone has a 16-volt differential analog output, which feeds into our 16-bit ADC. This ADC is sampled a little over 2,000 Hz, and it requires an input voltage of about 0 to 5 volts, so a feedback circuit helps control those signal parameters. Moving on to the resolution of Glinda. Earlier we talked about how our target resolution was about 20 millipascals to help handle the noise floor. And with the inclusion of a voltage divider circuit, we were able to get Glinda's resolution down to 1.4 millipascals. With Glinda's resolution being more than 10 times higher than our target resolution, this helps ensure that we'd still be able to pick up the weaker signals that may have otherwise been masked or overwhelmed by the noise floor. So now moving on to an event that Glinda was able to collect data on. This was a tornado event in Lakin, Kansas on the 21st of May of 2020. Here to the right, you can see a picture of the storm system that actually produced that tornado. The tornado happened about 8:24 p.m. local time, which is about 1:24 UTC, and Glinda was sitting in the storm tracking vehicle about 2.5 miles away. So this tornado was classified as an EFU because it touched down in farmland, so there was no observable damage that could be used to classify that tornado. Here we have the data collected by Glinda during that tornado event, processed with 100-second windows and 75% overlap. We pulled data 3 different times. We have the pre-event, which is at 6:45 p.m. that same day. We have the event, which is the tornado itself, and then we have the post-event, which is at 4:30 a.m. the next morning on May 22nd. So looking at the frequency decompositions, on this leftmost graph, we're comparing the pre-event in blue to the event in red, and you can see a significant swell in infrasound in the event data, centered around about 10 hertz or so. Moving to the center graph, we're comparing the post-event to the event, and it has a very similar relationship. And then moving to the right graph, we have the pre-event versus the post-event to establish that correlation between the two. Moving on to the second event that Glinda was able to collect data on. This was a severe hail event on May 22nd. This event happened in southwestern Oklahoma, and it produced very large hail about the size of a baseball. Even though there was rotation associated with this storm, it did not produce a tornado. Now moving on to the data collected by Glinda during that hail event. Here to the right we have the data for the pre-event, the event, and the post-event again, but all stacked on top of each other this time, processed with 15-second windows and 60% overlap. Notice there's spikes in the 50 hertz region and the 80 hertz region roughly. However, there's no significant rise in infrasound for all 3 sets of data. But this storm did not produce a tornado. So in conclusion here today, we've talked about a mobile infrasound microphone, which we call Glinda, whose mobility offers several advantages to analyzing severe storm systems. Glinda has successfully gathered data on severe weather events and will continue to do so as we move forward into the 2021 storm season. A few potential future work options may be real-time processing tools as well as monitoring other infrasound sources. And that brings us to the end of my presentation today. I'd like to mention really quick that this work was supported by the National Oceanic and Atmospheric Administration. Thanks for sticking around until the end, and I will open the floor for questions if you have them. Thanks.